Hello and welcome to another presentation in the Alternative Technology Association's Sustainable Living webinars. My name is Donna Luckman and I'm the Acting CEO of the ATA. If you haven't heard of the ATA before, we're a not-for-profit organisation that for over 30 years been promoting sustainable living in the home, be that renewable energy, energy efficiency or water conservation. And the aim of the ATA is actually share that information with many people as possible. So one way we've been doing that is this series of webinars to get across to a larger audience different aspects of sustainable living. We're quite lucky today to have a fantastic speaker in Tony Isaacs. I'll talk a bit more about him in a second, but just a few little housekeeping things. We'll be having a presentation for about 40 minutes. At the end of that 40 minutes, we'll have about 10 to 15 minutes of Q&A. If you've got a question for Tony, if you go to the left-hand side of your screen, you'll see the little chat box that's on there. Type in your question down the bottom of the chat box and push enter or return, and then it'll come through, and at the end of the sessions we'll go through as many of those questions as possible. So we might just head straight into it. So as I said, we've got Tony Isaacs. If you haven't heard of him, he's a consultant with a wealth of experience in the sustainability field. He's a qualified architect. He's specialising in energy efficient buildings and has lectured on thermal performance. A few years ago, or might be many years ago, he worked at the Sustainable Energy Authority of Victoria and actually developed the first-rate energy rating software. He also has lots of different experience offering advice to all levels of governments on energy efficiency and sustainable buildings, looking at social determinants of energy use, managing energy retrofit programs for public housing, and even teaching building industry professionals the art of energy efficient building design. So without any further ado, I'll hand you over to Tony.
Terrific. Well, thanks very much for asking me along, and I'm delighted to make this presentation for the ATA, and I hope you will enjoy it. So we're talking about insulating homes today, and Donna's already said much of what I've done in the past, so I'll just skip this slide and get into the meaty bits. And I thought I'd start out with all the controversial stuff and get that out of the way. There has been a lot of hysteria around about insulation, primarily because of all the problems that occurred with the well, I've said dumb insulation program. I don't think I can call it anything else. It was a great policy, but it wasn't well implemented. And some of you might recall having seen a one-page spread in the Australian newspaper a couple of years ago about how insulation doesn't actually save energy at all. And what the author of that was talking about was a thing called the rebound effect. And rebound is where people use the better performance that insulation provides, and instead of heating and cooling their buildings the same way after they install the insulation, they heat or cool larger areas for longer periods. They heat to higher temperatures, cool to lower temperatures. Now, there has been really little evidence of heating larger areas or to higher temperatures and that sort of thing in Australia. Certainly in the 1980s, the Victorian Gas and Fuel Corporation also sold insulation and had a great little scheme where you could pay it off on your energy bill. Went into people's houses and asked, did you heat larger areas? Did you heat to higher temperatures? Did you heat for longer periods? Some did, but more reduced the areas they heated, more heated to shorter times and more heated to lower temperatures, and the majority stayed the same. So there's not a lot of evidence for rebound in Australia. Certainly, though, in households who are living in energy poverty, putting in insulation can allow them to heat economically or cool economically, whereas they couldn't have done that before. And so they may not save any energy at all, but they will at least have some comfort. International studies of rebound effects show about a 20 to 30% loss of savings. In other words, insulation 70 to 80% effective, which I think actually should have been what the story in the Australian was about, not about the 20 to 30% of savings that can be lost. The other thing that I thought too was that a lot of those studies of rebound have come from a time of low energy prices. They're pre-greenhouse effect concern. It's before Lord Stern released his report. It's before Al Gore globe-trotted his message around the place. So whether people would be as blasé with their heating and cooling after they install insulation these days is not a matter. But the bottom line is, if you've got an uninsulated house and you put in insulation, the amount you save is up to you. If you want to use that improved performance to have a little bit more comfort, that's fine, but don't expect that you'll get the full theoretical savings that you'll see talked about in the trade literature and the promotional literature. Now, after the experience of the insulation program, there were a few houses that burnt down. And the reason is that if you wrap insulation around something that's very hot, things might catch fire. The answer to that is not to put things near things that are hot in your ceiling. So around halogen downlights, flues from heaters, keep them away from exhaust fans and that sort of thing. If you do that and you do it to Australian standard, the 50 to 100 or so clearance around those hot things, then your home won't burn down. Better still though, try and not have lots of hot things poking through your ceiling. So if you've got halogen downlights, well, they're pretty energy inefficient too. So replace those with LEDs or compact fluoros, and you'll alleviate much of the problem. If you can't do that, and you do need a licensed electrician to do that downlight replacement generally, then there are a variety of downlight covers, and I've got some photos of those later in the presentation so you can see what they look like. Those allow you to install the insulation right up to the downlight. The practice after the insulation program was basically to leave out a half a batt per downlight, and that resulted in your insulation becoming Swiss cheese, full of holes, and that significantly diminishes its effectiveness. The next issue about insulation is maintaining safe practices when you put it in. If you're going to put it in yourself, there are some really good manufacturer's instructions about installation, and I get to those a bit later. But basically, don't put it in when it's really hot, and follow all your electrical safety requirements. Make sure you're well covered, and you should be fine. A lot of the problems with people terribly, tragically dying during installation was to do with reflective foils and putting that on the top of the ceiling joists. The real tragedy, in addition, was that over 20 or 30 years, dust will build up on that top layer, and depending on how dusty your location is, could well render it ineffective. So I wouldn't recommend that as your only insulation in your roof. The other thing that's been bandied about is, isn't fiberglass the new asbestos? Well, I'm not an expert, but what I hear from the industry is that the actual fibre size is much bigger than asbestos, and that's significant. Also, the fiberglass is actually biosoluble, which asbestos wasn't. So the fiberglass industry and the glass fibre insulation industry tells me that it's not an issue, but of course there are lots of other products out there, and if you're really worried about it, then by all means select the product that's right for you. There are pluses and minuses with all products, so if you feel more comfortable, that's your choice. But what I hear from the glass wool industry is that it isn't an issue as it is with fiberglass. There have been a few cases of people having cancer from fiberglass, but those have been found in boat building industries where they've been sanding fiberglass all the time. Okay. So I'm going to start with a little bit about how insulation works. That's relevant because different sorts of insulation affect different types of heat flows. And when you want to compare between different types of insulation, having a little bit of background helps you to understand what's going on. All the insulation manufacturers want to sell their product ahead of everyone else's, and so hopefully this information will help you sort a bit of the wheat from the chaff here. So firstly, how does heat flow? And I'm looking at a ceiling here. Firstly, there's radiation. Now, if you've boiled the kettle but you can't remember whether you switched it on or not, you hold your hand close to the kettle. And you don't have to touch the kettle to know, yes, it's boiled, it feels hot. That's simply radiation. In the context of a ceiling, if you're heating your room, it's nighttime outside, the warm ceiling will radiate heat up towards the underside of the roof. And then there's convection, which is simply hot air rising. So in that same situation, you're heating the room below, it's nighttime outside, the surface of the ceiling is warm, the air in contact with that is heated, and it rises. So I'll just get a little laser pointer here. So here we go. The hot air rises, it comes in contact with the cooler roof, it cools down, and therefore it starts to fall, where it hits the ceiling again, and so you get this convection current happening, and that accelerates the heat flow. And there's also, I've got to do this one. And there's also conduction. And here I've zoomed right in on a little layer of plasterboard, and you'll see the bottom side of it is getting heated, and that heat's transferred through the material up into the ceiling. And the typical explanation of this is you've got a log fire, you've got a metal poker, you poke that into the log fire, and after a few minutes, the poker is hot all the way along the length. That is conduction heat flow, and that flows from the heat source up the material itself. So conduction is about heat transfer within a building material. So why is all that important? Well, different insulation products affect different heat flows. Bulk insulation, so batts and boards and blankets and blown-in, primarily affects conduction, but it also affects radiation and convection. If you put insulation on the ceiling, then the surface temperature at the top of the insulation is a lot different to the surface temperature of the plasterboard had the insulation not been there. Because you're affecting that surface temperature, you're affecting the convection and the radiation too. Reflective insulation, so your shiny foils, primarily affect the radiation. But if you put reflective foil under your roof, the temperature of that reflective foil will be a lot lower than the roof tiles, say in summer. So because of that, you're also affecting the convection heat flow and so on. Some insulation products will say, look, we stop 95% of the heat. They're often referring to just one of those modes of heat flow. All of them are engaged. So the way to compare insulation is by the R value, or its thermal resistance, its resistance to heat flow. For the same R value, you get the same effect regardless of the type. Now, I've gotten a bit confused with my Australian New Zealand standards numbers here. I think there's an installation standard that I've referred to as 4859.1 as well. The 4859.1 is the product standard, and the installation standard, I think, is 3999. And if anyone from the installation industry is listening, please send a message. Thank you. Always check that your insulation is actually manufactured to the appropriate standard. Now, bigger manufacturers test to the standard regularly, and this gives you a little bit more comfort about you getting what you paid for. That doesn't mean your smaller insulation manufacturers don't produce good product. It just means that they may not test as often for it. So you're making a trade-off. When you're picking someone who's not necessarily doing things under Australian New Zealand standards, you don't know for sure that the insulation R values they report are fair dinkum. For bulk insulation products, though, they report the R value of the product itself, and that R value is pretty much the same whether at Hobart or Darwin. But with reflective insulation, because it only works when it's facing an airspace, and it works by increasing the R value of that airspace within a building element, they talk about a total R value for the whole building element. Now, to compare with your bulk insulation, so you've, for example, got a brick veneer wall with reflective foil in it. But the R value that the reflective foil industry generally reports is the total R value for the whole wall. So that includes the bricks, the plasterboard, all the air spaces, and the air films either side. So to properly compare it, you take away what the R value of that wall would have been without the insulation. And for most building elements that are uninsulated, it's about 0.3 to 0.5. So that'll help you to get a better idea when you're comparing reflective and bulk insulation products. And as I said, reflective foil only works when facing airspace. If you have a layer, say, of anticon, as it's called, so a batt with a foil facing, and you install that with the foil facing down hard up against the ceiling, it won't add any R value. It's only if it faces an airspace that it works. And a lot of people get confused about reflective foil. It's not just reflective, it's also low emissivity. So if it's not facing the heat, that doesn't matter because it won't emit the heat on the other side either. Now, the emissivity of foils is tested and is usually in the range of 0.03 to 0.05. For an anti-glare coated surface, it's about 0.1 to 0.3. The lower the emissivity, the higher the R value you will get from the product. The anti-glare coatings are there to protect workers while they're installing the product. Workers on an attic roof putting up reflective foil, wearing shorts would get sunburn on their legs. So the anti-glare coating has been put there to reduce that. When you install a foil product in a flat or a sloping position, it has a lower R value for heat flow up because it works in the same direction as convection. It works with the property of warm air to rise. It's got about double the R value for heat flow down, where it's working against convection, against that property of air to warm air to rise. That means you get a different R value for different climates, depending on what the direction of the heat flow is, and also because the amount of radiation heat flow depends on the absolute temperatures either side. The lower the temperature difference, the higher the R value. So do be careful when you're reading literature for reflective foils that you're looking up the R value that is appropriate for your particular climate. So if you are looking for, say, heat flow up, that would be a ceiling in a cold climate. If you're looking at heat flow down, that would be a floor in a cold climate. Similarly, heat flow up in a hot climate, it's cooler inside where you're air conditioning, it's warmer outside, the sun's beating down on the roof, so you're concerned more with the heat flow down. Heat always flows from hot to cold, so heat flow down in a roof situation. Where you've got multi-layer foil products, you get a better R value than you would, not simply because you've created multiple layers, but because the temperature difference across those layers is less. The more layers you've got, the less temperature difference, and the lower the temperature difference, the less your radiant heat flow. And as I said before, you'll see a lot of literature about, well, I've seen it in the past, I don't know if they still do it, but they say reflective foil stops 95 to 97% of the radiation, but there's conduction and there is convection too. So do take into account that they're only talking about one mode of heat flow and not all of them. Okay. Bulk insulation works by trapping air in steel layers or cells, and air is a good insulator. Cellulose products made from recycled paper also have some R value in the actual material themselves. Different products give the same R value at different thicknesses, and generally, the higher the R value for a given thickness, the more expensive the product. So, if you've got lots of space, like ceiling facing an attic, thickness is not critical, feel free to choose the one that's a bit higher, has a bit greater depth to give you that R value. Be careful though that your framing, particularly if it's metal, can significantly reduce your R value if you've got something that's really thick there. If you've got limited space though, like in a wall, then choose the product that gives you the R value you need. I give some recommendations for the absolute minimum R value I'd use in any wall or ceiling or floor throughout Australia. You can exceed those if you want to, but generally that will allow you to use the cheaper products too. Bear in mind that if you've got limited space and you compress an insulation batt, that firstly use some of the R value. So let's say you've got 110 mil batt you're trying to squeeze into a 90 mil space. Firstly, you lose about 10% of the R value. And secondly, if you compress it too much, the pressure can eventually pop off your wall linings. So do be careful that you don't compress your insulation too much. Remember too that you've got a loose fill that will settle over time. So when you're looking at its reported R values in your trade literature, if they don't talk about the lifetime R value, take about 20% off. And here I've given a little graph showing different types of products and the R value they give for different thicknesses. I've got a little chart here, and I believe the presentation's available for download. This shows you how much R value you lose with glass fibre products when you compress them. So here I've got a case of, I've got 110 mil insulation original thickness. I've compressed it by 20 mils, so you project up from 110 to the amount of compression, and you go across to the axis on the left-hand side, and that tells you how much of the original R value you're left with. So in this case, 110 mil compressed by 20 mil gives you around about 90% of the original R value. So, how much should you put in? Well, in new homes, there's two different ways of meeting regulations. You can get 6 stars using an accredited nationwide house energy rating analysis tool, so Accurate, First Rate 5, or Burrs Pro. And you can use any insulation you like that will work. Generally, in cooler climates, you can't get away with much less than R3, and in warmer climates, you can't get away with much less than about R2. Or, if you don't want to do an energy rating, and I'd recommend to everyone that you do, because it gives you a better overall assessment of the design of the house and not just the performance of the elements. But if you do want to use the elemental standards, then you'll have minimum R values for walls, floors and ceilings, and they'll range from about equivalent of adding R4.5 up to say R6 in alpine areas. But if your house is a passive solar plan or high-performance windows or just small window areas, if you use an energy rating tool, you can get by at much lower R values than you'll see in those elemental standards. But I think, why not put as much in as you can? Why not exceed 6 stars? Because let's face it, 6 stars new housing is not going to deliver 80% emissions reductions that we're after, or maybe even more. And the extra cost of putting in more insulation is small. You're only paying for a little bit of extra material. The install's already there. Energy prices are rising well above inflation at the moment, and that will continue, as far as I can tell, as we switch over to renewable power generation, which means the investment you make in saving energy is worth more year after year. And if you want to go the whole hog of going carbon neutral, it's a lot easier to do. You'll need to put in less PVs. The higher the star rating of your house and higher levels of insulation are one way of getting to those higher star ratings. I should add at the start, I did talk about, I have done a fair bit of work for the Insulation Council of Australia and New Zealand. I think it's important for me to disclose that, just to be transparent. I don't favour any particular insulation product. It's the insulation as a generic thing that I'm very much in favour of. And there's different strokes for different blokes, but I thought important that you know that, yes, I've earned some money from the insulation industry and from one particular section of it, the glass fibre insulation. Now, one of the things that is typically done to assess how much insulation should you put in is to compare the installation cost with the present value of energy savings over 40 years. Now, present value is simply a way of discounting, your saving from your 40th year to say, well, what would that be worth in today's terms? And on the graph I've given, here is the cost of insulation. Here is the cost of the energy over 40 years. And you add the two up and you search for the minimum point, and that tells you, in this particular case, that about R1.65 would be the best, the lowest total cost. But the thing is, your optimum zone, where costs are pretty much equivalent, is very broad for insulation. And the faster the price of energy goes up, the broader this zone becomes and the higher the insulation level you can afford to put in. So it's not like if you put in above the recommended perfect optimum that you're losing a lot of value, that you're paying a lot more over time. The costs are very similar from about R1.5 to R4.5. So in this case, I think this is for wall insulation, there is a limit, of course, to how much insulation you can put in a wall. But clearly, in terms of the best solution, you're not nearly as constrained as you used to be. Way back when the first Australian recommended insulation standard, recommended R-value insulation standard was done, these curves had a very defined optimum value. The curve was much steeper either side of the optimum. These days it's not the case. So how much is enough? Well, at least R4 in your ceilings right throughout Australia. More if it can fit in there, taking into account that, yes, I've got some compression and that sort of stuff that might happen and you want to avoid that. If you install insulation under the roof, it's actually less effective in cooler climates than if you put it on the ceiling. The reason being is that attic spaces are very air leaky, so that the air temperature above your ceiling, almost irregardless of what's under your roof, will be around about air temperature. So much better in cooler climates to install insulation directly on the ceiling. There is concern with insulation in hot climates that you create a hot box by putting in insulation. and the conventional wisdom has been to avoid putting in insulation, but the reality is that insulation stops the heat coming in a hot climate by more than it stops the heat going out. In an existing home, though, if you've got big west windows, you can get a hot box effect. So it pays very much to shade those windows, install some awnings, or even just some shade cloth on a roller to make sure if you're putting in insulation that you don't get a hot box. But the general rule is it stops more heat coming in than it slows the heat going out. In walls, I'd recommend at least R2. And it can also help in internal walls to unconditioned spaces, particularly garages, but also bathrooms and so forth, or any wall that backs onto an attic space should actually be insulated to the same R value as the ceiling. And the wall insulation you put in depends on what's on the other side of the wall. So here we've got a split level house. This part of the wall faces the outside, and I'd recommend putting in R2. This part of the wall is in between rooms, and unless the rooms are unconditioned, I wouldn't put insulation in there. This part of the wall faces the subfloor space, and I'll make some recommendations about how much insulation you should put in the floor a bit later. But you should insulate that wall to the same level of insulation as the floor and the rest of the house. Another case where a wall is really a ceiling from a heat flow point of view is I've got a cutaway here of a roof. Here we've got a piece of wall abutting an attic space of a single-story section. Again, you should insulate that as if it were a ceiling. So where I said R2 in walls, not here. Put R4 in that. Now, floors are tricky. It depends on how much heating and cooling you need in your climate, because floor insulation definitely lowers the amount of heating you need, but it increases the amount of cooling. A subfloor space is generally a lot cooler than the outdoor air temperature. So if you put insulation in your floor, you're reducing the amount that your building can cool off. And think about it, where does the dog go on a hot summer's day? Underneath the house, because that's where it's nice and cool. Insulation under a slab can be a good idea, and you'd use a waffle pod system there, typically to insulate the slab. But it also will make performance worse in summer. So if you're in a predominantly cool place like Melbourne or Canberra or Hobart, using waffle pod slabs, if you've got a slab construction, or if you've got a suspended timber floor, using R3 or so is a good idea. Mild places like Sydney and Perth, I'd actually recommend, if you're building a new home, get your energy rating assessor to simulate a few different options there to see what the impact is on summer and winter. If your main concern is to keep cool in summer, then probably avoid it. But generally, with some draped foil, using breather foil with little holes to allow the moisture to escape, is a reasonable idea for those milder climates. But remember, reflective foil only works when it faces an airspace, and that airspace is sealed. So at the ends of your floor joists, you need to block off those ends to make sure that those air spaces underneath the floorboards don't have air exchange to the outside. In hotter climates, from Brisbane to Darwin, you can insulate the subfloor walls. That makes the underfloor a little cooler, and so increases because you don't have as much heat transfer from outside through the subfloor wall. So that's a good strategy. It probably has about half the effect if you insulated the whole floor. But that is one thing you can do. You'd want to use a board product that's resistant to moisture because it's in the subfloor. In hot climates, though, if you've got a floor that's elevated above the outdoor air, say on your second floor overhangs your ground floor, then using at least R2, because there your heat's flying from your cooler inside, or sorry, from the warmer outside air that floor is exposed to into the cooler air inside where your air conditioning. In existing homes, it's a little more complicated. A lot of people will have insulation there, and it may not be all that great. It's very tempting to want to top up the insulation, and certainly even if they had existing insulation. But remember, 70% of the benefit of insulation comes from the first R1, so the economics are not nearly as good for top-up insulation. If you're really tight with money, a more efficient heater or cooler or hot water system is possibly a better use of that money. But if you can get a government rebate for doing it, that changes the economics. If you're able to install it yourself, and it's a rotten job, installing ceiling insulation, I'd rather leave it to the professionals myself, having done it a few times in my own houses. But there's no doubt it's cheaper. So if you're getting a rebate, by all means. If you can install it yourself, by all means. But if you just want to try and do your bit to the environment and make your house as good as possible, then go for it. But as a general rule, remember, you're not going to get the same extent of benefit that you get from top-up insulation that you would from insulating things there. With walls, it's tricky. Unless you're removing linings in existing houses, it's hard to get insulation into the wall cavity. There is a hydrophobic rock wool product that you can use that you can blow into the wall cavity. They have to drill holes through the top plate and noggings to do that. So that can be tricky. And it costs about 4 times as much as installing it, just batts in a new home. You also have to block off any way for the loose fill insulation to escape, so around wall and subfloor vents and other penetrations through the walls and at the bottom of the wall cavity. Tricky for weatherboard walls, as I say, you've got to drill holes not just in the top plate, but also the nogging at the halfway up the wall. But wall insulation can make a huge difference. I think in Canberra you get a rebate too for wall insulation. There are alternatives to pumping it in, and I refer to Alan Pears here, one of regular contributors to Renew. If you're replacing some weatherboards, then put a couple of bulldog clips on your insulation, attached to some string, and you can drag it down through the cavity, take off another weatherboard just above the noggin, and you can drag it down to that level. If you are replacing linings, it's easy, of course, but the patented Pears method, the bulldog clip and the string, works just as well. If you cut a strip just below the top plate, just above and below the noggins, and just above the bottom plate, you can just patch the plaster after that. So you attach the bulldog clips, bit of string, drop the string down, and then start to pull the batt through, and that works pretty well. Floor insulation in existing homes, the same caveats as before. Good for heating, not so good for cooling. So it's best in cool climates. And I should add that insulating a subfloor is the worst job ever. Spiders, mice, confined spaces. Yeah, I've only done it once and I wouldn't do it again. Bear in mind though, if you're removing carpet, you're removing some useful insulation. Carpet and underfelt would be worth about R.3. So if you like the polished timber floor look, think about putting in some floor insulation if you've removed the carpet in a cool climate. If you're using a floating timber floor, on top of your flooring, and you've got a suspended floor over a subfloor, or you've got a floor which is elevated and exposed to the outside, then you can put in an extruded polystyrene underneath your flooring. It has to have sufficient compressive strength to not cause a problem. When you drop something on it, like a fridge, but the insulation won't crumple underneath it. And there are also some new underlay products with higher R values. So there are other solutions for insulating floors to existing homes that you can look at, but as a general rule, keep to the sorts of levels that I talked about previously, and look at some different ways of doing it, not necessarily under the floor, but perhaps under your flooring product. Now, I've already gone a little bit over time, but I'll just spend 5 minutes on installation. A lot of this stuff is in the installation guides that your manufacturers will provide. I've borrowed a few of the illustrations from Fletcher Insulation for this, and thanks very much to them. For their installation guides are available on their website. Now, the pictures you see here are taken with infrared cameras, and they show the temperatures of the walls. And you'll see that around here, the installation of insulation, where my laser point dot is moving, it's a different temperature. That's because the insulation wasn't installed very well. You can see here the different temperature of the framing members compared to the insulation. Framing can be a bit of a thermal break. If you've got a steel frame, there are little products you can get to provide that extra thermal break that reduces the heat flow through the framing member. But you'll see here too, there's some green and blue, which is a cooler temperature, because they haven't installed right up to the top plate, and they haven't installed right up to the end stud. And this can be quite important in terms of the effective R value that you get. Another case, I've got the big arrow pointing there. You can see at the top of the wall, they didn't install right up to the underside of the top plate of the wall. And the basic thing with insulation is don't leave any gaps, except around things that generate heat. Another case, I think this is an American house where they've insulated the under the roof. It's got a habitable room upstairs. You can see all the heat escaping around the flue, but you also see around the ridge line, they haven't insulated all the way up to the framing. Always important to insulate all the way up to the frame. And if you're doing it yourself, gloves and goggles, breathing masks, wash after you put in, and if you've got some offcuts, dispose of those responsibly. Batt products come in standard sizes, generally 450 or 600 wide, or to fit between a 450 or 600 centre framing. If you don't have framing at those centres, then you need to trim batts and fill in the space. Now, I think 4859 is the material standard, and I think 3999 is the installation standard. But the focus of the standard is around safe installation around things that are hot, reducing thermal bridging so you don't leave any parts uninsulated, and maintaining the insulation performance, so keeping it dry, protecting it from moisture, restraining it if it's going to be falling out during the installation process and so forth, and maintaining sealed air spaces so that your effective insulation works. I've got a few little illustrations here about installation around hot things and ceilings, and I'll just skip through these for the time being. At one stage, they did require 200 mil clearance to a downlight. But that's gone back now to 50 mils or thereabouts. And this is a little example that I wanted to get to, and I'm probably finished just about here. This shows your installed R value, shows the number of downlights per 10 square metres in your ceiling. If you've got a 450 by 450 gap, in other words, half of that left out per downlight. So if you've got 4 downlights per 10 square metres, you installed... No, sorry. I should take my glasses off so I can see what I've actually done. This is the R value installed. This is the number of downlights per 10 square metres. So we've installed R4. We've got 2 downlights per 10 square metres. Leaving out 450 by 450 per downlight means you actually only get R2. That's a really graphic illustration of why it's important to keep those gaps to a minimum. This is what happens if you've got a downlight cover. And you see same number of downlights, same R value installed, but effectively about R3.8. Here's some of the downlight covers that you can get up there on the market. Some of them you can install right up to, some of them they claim you can install over the actual downlight itself. And I'll just go through. If you've got old electrical cabling, you need to put in a separator so that that electrical cabling doesn't get too hot either. Important to extend your insulation over the edge of your wall if you're putting it in the ceiling. A little detail here for what you do where you've got a cupboard with a lower ceiling. And I think I'll leave this. If you're putting in loose fill, important to restrain the loose fill from falling down the wall cavity, and you'll see a little illustration there of where that's got to go in. You can use a batt for that. I'll just skip over that one because we're getting close. This is a photograph from a real house of half of that being left out, range of downlight. They've also left the transformer on the plasterboard. The transformer gets hot. You shouldn't do that. So don't do that. Cut it neatly around the downlights. Be very, very careful in terms of your electrical safety. Keep well away from any wires and that sort of thing. If you're using loose fill, then they use a little restraint that goes around the downlight. You shouldn't squash it up if you're near a frame. Remember too that there is a minimum distance required between downlights and frames. Manholes are often forgotten about. Pop a batt or a pillow of loose fill there and follow your manufacturer's instructions. There's a lot of good instructions available for download on the web from the various manufacturers. There's also the ICANN's insulation handbook, which goes into all the various ways you can comply with regulations. I'm a Victorian, so I know the resources in Victoria. There's a couple of really good little insulation data sheets from Sustainability Victoria, but most of state governments have reasonable resources. Also, the Your Home Guide, and I've given the website URL for their information on insulation. And I often don't read manufacturers' instructions when I'm trying to put something together. I've successfully put together a lot of IKEA furniture without looking at the instructions, and there's only been a few bits left over. But the manufacturer's instructions for insulation is something that you should absolutely read, and I'll leave it there. Thank you. Now I think we're having questions, and Donna will tell me what your questions were.
Yeah, thanks for that, Tony. As Tony mentioned, this presentation will be available on the ATA website afterwards, as well as the webinar will be able for viewing again on the ATA YouTube channel, but we'll send you through those details. So we've got about 10 minutes for questions. I'm just going to go through a few that's already come up through on our chat screen. Just the first one, Tony, from John Kay was, should you install extra batts over the current ones?
If you don't have much batt there, you can do that. As I said in the presentation, it won't be as effective as if you put in insulation from having none. So the economics aren't as good, but if you want to make your house as good as it can be, then absolutely. But think of what's the R value or thereabouts of the product you've got, and you'll see that little graph I've given for R value per 100 mil thickness. So if you've got 200 mil thickness, you can double that. If you've got 50 mil thickness, you can halve that. Look to make it up to at least R4, and that'll tell you what sort of batt to put in that gives you enough R value. A lot of times too with existing installations, they're not installed terribly well. There's lots of gaps and that sort of thing. So top-up insulation can be really handy simply because you fix all the problems in the installation of the existing insulation.
Well, thanks for that, Tony. Got another one from Beth S. I wonder, what would you recommend for insulating a corrugated iron shed, wanting to insulate and line this to make it into a study guest room?
Yep. Well, if you're lining it, it's basically, well, what will fit in between the lining and the corrugated iron. If it's a shed and it's just a guest room that isn't going to be occupied a lot, then put in as much insulation as will fit in between your corrugated iron and the lining. Maybe you might allow it to compress 10 mil or so. Then I'd be flexible on having to have R4. Mind you, if you want to put in extruded polystyrene, you certainly could get to R4 with a sort of thickness of the framing as you've got, and they're very good with waterproofing. And if it's an old corrugated iron shed like ones I've got in my backyard, you do get the occasional leak through that, and so having something that's resistant to moisture would be good too.
Cool, thanks. You got another one here, following up our previous one. If you have existing loose fill insulation and are looking to upgrade, should you remove it completely and install new batts, or just install new batts on existing loose fill?
Yeah, that's a tricky one. I'd certainly install new batts around the edge, because that's where it's going to blow around, and that's where there's a danger of it dropping into the wall cavity. So absolutely put the batts around the edge to restrain it. If you've got a very windy attic, it can tend to blow from one side to the other. I might think of taking it out altogether then. Loose fill is problematic because it hides what's in the ceiling. So there might be wires there that you can't see and that sort of thing. So I'd be very careful in taking it out, but it certainly, if it's been there for 30 years or so, and it's below the level of the joists, I contemplate taking it out, but you can always put in R2 batts on top for a start, see how that goes, and then if your experience is, well, no, look, the ceiling feels hot, it's just not working well enough, then come back and put in a load of R2s if you're doing it yourself. If you're getting someone to do it, then you want to put all that insulation in the one go. As a general rule, I probably wouldn't take it out altogether, except if you've got a windy attic, and you'll see, the loose fill will be sitting to one side of your roof. So under that sort of situation, I probably would. And if it's really, really old and there's not much of it, might as well.
Oh, thanks, Tony. No one here from Peter M. Is it possible to
did some work on, if you've been watching Grand Designs, on the Balfritz houses, and they have about 300 mil of insulation in the walls alone. They were rating at about 8 stars. So I don't think you can have too much insulation within the physical constraints of your actual building elements. You try and put R5 into a 90 mil stud wall, and as I said, you'll end up popping off the plasterboard. Certainly there's a point at which you don't get very much benefit at all, and that's probably for a ceiling in a mild climate, it can be at around R5. in a more severe climate around R6. But look, I've certainly visited a few straw bale homes that have got a foot of cellulose in their ceilings, and they really are very good houses. So I don't think there's a problem with over-insulating. It's just that with every R1 you add, you're getting less and less benefit.
Thanks, Tony. We might just have time for one more. I know we've got quite a few questions there. So what we'll do, we'll set up on the ATA's forum on our website, we'll set up an insulation webinar follow-up, and we'll be able to do a bit more of this Q&A afterwards as well. Yep. Just one last one. This is from Peter M. What do you think of straw bale walls as wall insulation?
I think the conservative value that is used in energy rating programs is about R5. I think when they first go in, they might be even higher than that. The stuff I've seen from the States has actually measured some new straw bale walls at about R8. So when I've said, about R2 in the walls, if you've got straw bale, well, you've got at least 4.5. Probably more. But there hasn't been a lot of work done in Australia, so I'm a bit loath to transfer an American straw bale R value to an Australian straw bale because I simply don't know about the density and the nature of the material.
Oh, thanks for Tony. And we might have to wrap it up there. So there's quite a few other questions. So I think, Tony, you've accumulated quite a lot of people's thoughts on insulation and also knowing so much knowledge that you have accumulated over the years. So thank you once again for sharing that with us.
My pleasure. And happy to help out with some of those questions too.
Great. Thanks, Tony. Just as once again, this is a presentation by the Alternative Technology Association, a not-for-profit who promotes sustainable houses and renewable energy and energy efficiency. You can gain some more of this type of information in our two magazines, Sanctuary and Renew magazine, and you can even join up as a member. So for starting from $75 a year, you can get access to our free advice service as well as all the back issues of our magazines online for free as well. But our one thing that I was about to mention about back issues is that Tony mentioned the Allen Pierce patented bull clock clip method of installing insulation into walls. We actually did an article of that in Renew magazine quite a few years ago, so we'll put that article up on our website as well. This webinar would not be possible without the support from bankmecu. They've been a partner with us for quite a few years, and we thank you for helping us put on these webinars. If you have not heard of bankmecu, check out their website. They have quite a lot of different financial packages that actually help people put in place sustainable technologies and help with their renovations of buildings in their own homes as well. As I just mentioned, this has been recorded and will be going up onto the ATA YouTube channel. And before we're about to say goodbye, we'd like to thank you all for joining us today, and we'll be sending you out a survey as well just to get your feedback on this webinar and also to get some topic ideas from yourself or what you'd like to see for future issues. So thank you for your time today.